Bastien is going to talk about capability safety in the presence of indirect sentries. Again, we should have a few minutes for questions at the end, but I'm tightening things a little bit per speaker, so we should hit lunchtime on time. Thanks very much.
Okay, thanks, Jan, for the introduction. So I will present you joint work with Aina, Linn, Lars, Pichon-Pharabod, Dominique, Devriese, and Lars Birkedal about proving capability safety in the presence of indirect sentries. So one of the points of capability machine is to enable mutually distrustful programs to work together. And by working together, one of the things is to be able to communicate between each other and to share, for instance, pointers. And the way that it's done in high-level language is by using function calls. But function calls are challenging. They are challenging in two ways. They are challenging in design because you want to make sure that the coding conventions that you will design, ensure the security properties that you want. And they're also challenging to formally reason about because it requires a lot of logic to do such. Especially because you might reason with unknown code. So at assembly level, the way that we distinguish between function is by using some encapsulated closures. With capability, you can create such encapsulated closures. So there is two ways. One way is to use sealed pairs, and sealed pairs are quite expressive because you can link one code region with one data region, and you can actually create different data regions with the same code. And another good point about sealed pairs is that it follows the principle of least privilege. You can only share the code and the data that you want to share with. But it's especially hard to reason about because it requires a lot of bookkeeping for every O types that are involved in the pairs. Moreover, it's also quite limited by the number of O types that are available in the machine. And for instance, in Chariot, there is only a very limited amount of O type, and you cannot really rely on them to create sealed pairs. Another way to create closures is to use sentry capabilities or direct sentry capabilities or entry capabilities. This is all different names that I might use a bit randomly in my talk, but that means the same thing. And one good point about the entry capabilities is that we already have a mechanized proof of capability safety for such capabilities in the John et al. Work. The problem is it requires some tropline code that mixes code and data, and it means that it breaks the principle of least privilege because it requires some region that has both the write and executable permissions. But actually there is a third way to create closures with indirect sentries. And indirect sentries is currently a proposal in the Cherry ISA, which is supposed to facilitate the closures with a fixed entry point and a fixed context. And the main advantage of this is kind of work as the direct sentry, but it does not require any trampoline code that mixes code and data, and then it enables the principle of least privilege. So in this work, what we do is that we conduct a formal study of indirect sentries, and we try to see, can we prove like set good properties about it? More precisely, what we do is that we extend series, which is some sort of mini Cherry machine with indirect sentries, and we aim to facilitate the expected reasoning principle and the expected security guarantees. And in particular, we aim to show that we still have capability safety in this context, and as a reminder, capability safety is strictly stronger than capability monotonicity. Moreover, what we do is that we prove robust safety of a secure calling convention that does not require any trampoline code because we use indirect sentry. Moreover, all of this work is mechanized and machine checked in the COG proof system. Okay, so I talked about indirect sentries, but what are indirect sentries? Or more specifically, I should talk about what are the points to pair indirect sentries, because the Cherry ISA proposes two flavors of implementation for the indirect sentries, and we only focus on this work about the points to pair. So if we have an indirect sentry here on the left part of the slide, we have a special permission that says this capability is an indirect sentry that has the authority over the bounds between B and E, and that currently points to the address A. And this capability is immutable, and the only way that you can use it is to jump to it. What happens when you jump to the indirect sentry is that it will load the first word of the capability in the PC, and then it will load the second word of the capability in the IDC register. And the IDC is just a name for a regular register that aims to receive the data word. So in this slide, I put like code capability and data capability, but it doesn't have to be capabilities. It can be like any words. So to formally reason about this, we follow the methodology of Jordan et al., which consists on three things. The first one is that we extend the open semantics, which I recall is some sort of mini cherry machine. And the main point of having this mini cherry machine is to make sure that we can make the proof more tractable and to only focus on the essence of the indirect sentries and on the machine. Moreover, I talk about calling convention, but we don't have any specific region for the stack. And I will only focus on like heap-based calling convention. And the reason is because stack-based calling convention requires some more features, such as the locality bit or things like this that we do not support in our version. Okay, the second bit that we need to extend is the program logic that allows to reason about known code in like a convenient way. And our program logic is very close to series, which itself builds on top of the iris separation logic. Finally, the third point is that we have a logical relation that allows to reason about unknown code, and the intention of the logical relation is to capture capability safety. The combination of the program logic and the logical relation allows to reason about interaction between known code and unknown code. And this is the bit that is specifically challenging because, as I said, it requires to reason about unknown code. So for the first part, I already gave you like an informal way of how indirect sentry works. For the second part, I won't develop more because we won't need it in this talk, but I will try to give you at least an intuitive idea about how the logical relation works and about what it captures. So if we take the diagram where on the x-axis we have the time of execution since the beginning of the execution of the machine, and on the y-axis we have some sort of abstract representation of the authority of the machine. Higher doesn't mean more authority, it just means a different like set of memory, for instance. So we can say that at some point, at some domain, the authority can only decrease, and then at some point we do a jump and we completely change the domain, and it performs domain transitions. So for instance, capability monotonicity stops at domain transition, and then it does not capture more than what happens after the jump. And the goal of our logical relation is to be able, indeed, to capture more. And to do so, there is two components. There is the V component that captures what is the authority of a word that we give, and then the E component that captures what happens after the jump. And in particular, what is very important about this logical relation is that it needs to be defined in a way that is compatible with the user-defined invariant. So for instance, if we have an address A that has an invariant saying that the content is always non-negative, then when we will define V and E, it needs to be compatible with this. I will go a bit fast on this slide because we are a bit short on time, but one of the main novelty of our logical relation compared to series without indirect sentries is that we need to reason about two different words when we do a jump. One that will be loaded in the PC, and the other one that will be loaded in the IDC. And what we show with our logical relation, the main theorem is that if we jump to unknown code with the current context that only the current register file containing only safe values, then it is safe to execute, and it will not break the existing invariant. Okay, so I don't want you to understand everything on this slide. I just want you to point out that our extension is not trivial in the way that if we look at what was the definition of safe to share for the regular sentry, it was just this line here. But if we look at what it is for indirect sentry, there is a consequent amount of definition more. Okay, so now that I said, okay, we can use the logical relation to work with unknown code, how can we do that? And to do that, we define a heap-based secure calling convention that itself is an adaptation of earlier work of heap-based calling convention, but that used direct sentry and then require the trampoline code. So I will quickly show you how the calling convention works. So at the beginning of the calling convention, we allocate some space in the memory with a trusted malloc that will store the local state. Then we allocate another part of the memory that will contain the continuation pointer pointing to the return site and the data capability pointing to the local state. And this space of the memory will be part of the indirect sentry, which represents the return pointer that will be given to the callee. And we will clear all the other registers that are more parameters. The important point here is that when we do the specification of such calling convention, we need to show that when we jump to the adversary, every register contains only safe to share words, and in particular, this return pointer. Okay, so I claim that this is a secure calling convention, but how can it prove that this is indeed secure? And what do I mean by secure? The main properties that we reason about is local state encapsulation, and we don't have any formal definition about what local state encapsulation is. And to prove that this is secure, what we do is that we proceed by showing some example and showing that the local state is encapsulated on some example. So the example that we show is the so-called sub-buffer example that consists on we allocate some region in the memory, we store a private value, here is 42 in the buffer, and then we split the buffer into regions. One that contains the private value will be said private, and the other one is said public. The private part will be stored in the local state, and the public part will be shared with the adversary. On the formal point of view, what happens basically is that the private part will be somehow part of a user-defined invariant, and the public part will be shown to be safe to share, and this safe to share will need to be shown to be compatible with this user-defined invariant. Okay, so now when we jump to the adversary, we don't know anything anymore about what is the content of the public part, because the adversary could have written anything in it. But what we know is that in the private value, in the private part of the buffer, it didn't change. And because it didn't change, this is how we show that the local state was indeed well encapsulated. Okay, so to summarize this work, our main contribution was to extend series, which is this mini cherry machine with indirect sentries, and we designed a secure heap-based calling convention that does not require any trampoline code. And we illustrate some robust capability safety on some concrete example. As a future work, what we would like to do is we would like to combine this indirect sentry work with stack series that requires more features such as locality bit or the experimental uninitialized and directed capabilities in order to define and prove a secure stack-based calling convention that would ensure also well-bracketed control flow. So thanks for your attention, and I would be glad to answer any of your questions.
That's great. Thanks, Bastien. Do we have any questions? No? So I have one, which was about, you said initially the indirect sentries, they can cover a range, and within that you have a pointer to a pair of capabilities. One is code, one is data.
Yeah.
But you then suggested that's somehow general. It's not baked in that it needs to be code or data. So what can you do with the rest of that range, and also how much is built into either the series or the reasoning examples that actually it needs to be a program pointer and some data?
So as soon as you create indirect sentry, all the rest of the range is just unusable. And the only thing that you can do with your indirect sentry is basically like jump to it or like discard it. So usually when you create indirect sentry, we try to only allocate 2 addresses. And what was the second question, sorry? So
is it built into either the logic itself or proof examples that it is in fact going to be a code and a data capability?
So it doesn't have to be. One of our limitations currently is that in the logical relation, we require to show that if it's not a capability, it also has to work. It also has to execute. So we require that it also works if it's an integer, but we think that we can leverage this thing. But yes, we do not require anything more about the content of the indirect sentry. It can be like a regular integer or anything else. The main idea is that we try to delay as much as possible the errors, and at some point it will probably.
Okay, thanks so much. Matthew?
So you've taken the malloc as one of the things you need to build compartments. Should malloc be in a compartment itself?
So the malloc is, say, trusted, which means that we designed a malloc, which is, in our example, just a bump allocator, and it's trusted in the way that we have a specification, and we know that we can share it with any capabilities, and we need to access it in like the compartment. But it can be shared safely.
Robert?
Does the malloc not have private state that needs to be protected?
It does have a private state.
Okay, so I mean, it depends how you define compartment, but I think maybe the question Matt was getting a bit at was like, how do you protect malloc?
So we don't need the malloc to create a compartment, but we need it to use the connect convention. We cannot use the connect convention, it's just put down. And the private side would be still encapsulated.
Okay, thanks very much.